What's up, guys? Sim Science back at it again. You already know what it is. Up here talking about metallic bonding. Now, this is where my sweet new intro will go. If I ever. Oh, well, first step is I need to make a friend, and then if that person's good at that kind of thing, maybe I'll get an intro. But for now, let's talk about metallic bonding. Okay, this will be a quick vid. This is not a very complex topic. It's probably the simplest type of bonding to understand. The most crucial point I think is just that metallic bonding has some unique properties that make metals different. Okay, so I found some pictures online that are probably better than me drawing stuff. So we're gonna take a look at those. So this first picture right here, okay, this kind of shows you that sea of electrons idea that we've talked about. So within this metal, you have these positive ions, these cations of metal nuclei. Okay, so this could be any metal. I think I drew it on the board and called it iron. So you have all these nuclei here within this space. So this could be like I drew on the board. You can picture it as like a metal rod with these positive nuclei scattered throughout it. And then surrounding all of these are these negative electrons. Okay, so these electrons right here, all around these, and they're all sharing them. So that's what makes it a bond, is that these metal nuclei are held together based on the fact that they're sharing an electron cloud. So this description right here, electron cloud that doesn't belong to any one metal ion. So it's shared between all of them, and that's what holds them together. Okay, so metallic bond isn't two separate things coming together like a covalent bond or ionic bond. It's just a bunch of the same metal sharing these electrons. Okay, that's what metallic bonding is, and let's talk about some of the properties. So I took these pictures with the textbook and imported them in here. So first of all, the ability to deform a metal. So this is malleability. Malleability. Okay, so you can see here you have an external force in the form of this hammer. So if you picture this as a metal, you have your cations in there, and then you have the blue cloud around it is the electron cloud of shared electrons. So those electrons, like we talked about up here, they act as a sort of buffer between whatever's happening and the positive ions. So those ions exist in a sea of negativity. Sucks for them, right? Back to it. So you hit the metal itself, and you're going to dent it. You're going to move it like this, but these are the positive ions, the cations, are still buffered by these electrons that they just move. Okay, they readjust. Okay, so the metal ions move within it, and they take on a new shape. They don't snap, they don't break, but they adjust. The buffer of those electrons allows them to do that, maintain distance from each other so they don't repel each other explosively and just move. And we see that all the time. You know that if you had a thin sheet of metal, you could hammer it and change the shape because it is malleable. Malleability is key here. Along with malleability comes ductility, which is a very similar concept, and it's for the same reason that metals are malleable, they're also ductile. So ductility, the difference between malleability and ductility is malleability is more molding or hammering or changing the shape, and ductility is that too, but specifically ductility is stretching thin and long like a wire. So something that's ductile can be stretched into a wire, and we see that in metals all the time, like a copper wire. So let me see if my artistry can do a good job describing this. So I was going to tell you guys that I was uncomfortable because I'm in bed, but it's probably too much detail. My brother's going to comment again. Huh, Patrick? I hope he's watching right now, Little P. That's what I call him. His name's Patrick, Little P. Just that. Okay, so picture that you have a funnel like this. We'll make our metal gray. So you have a big bar of metal, and you're trying to push it this way through this funnel sort of thing. Obviously, it's going to be a really hard funnel. So you're pushing this block in. So we'll elongate it so it's getting pushed this way. And as these get here, this funnel surface is kind of doing what the hammer did. It's bending. It's gonna shape this metal and push it this way so that it gets pushed through here and it lengthens. So it's all gonna reshape because the sea of electrons allows it to do that, and it's gonna come out as a long, thin strand. Okay, so that's what ductility is basically. The ability for it to be stretched thin, again, for the same reason that it's malleable. Okay, so to give you context for why that's unique, this is another picture I took from your book about ionic compounds. So I showed you this on the board, but I think this picture captures it better. So ionic compounds, you have positive atoms and negative atoms attracted to each other and existing because those charges bring them together. But if you apply force to something with ionic bonds and you move, like you see here with this picture of the hammer, so you move this positive ion down so that it's now even with another positive ion, and this negative ion's even with that negative ion, these are going to repulse each other very strongly, and that's why things snap. That's why things break. That's why you can break things. That's why if you hit glass with a hammer, it's going to break. Okay? Or anything that shatters, this is the reason why, at the molecular level, at the atomic level, even smaller than that. Okay, and that's why you couldn't take something that was an ionic compound and put it into this ductility thing, because when it would get up against the funnel, its bonds would move and it would all just break because they would repel each other. Okay, so that's what's different about metallic bonds. It makes them malleable and ductile, and then the last thing is that it makes them good at conducting electricity. So I'll go over there in a second, but I'll write it down first. Good conductors of electricity. Because electricity is just the movement of electrons. Okay? So that's what electricity is. It's electrons moving as energy, basically. So when you have this big sea of electrons here, if you had a bunch of electrons come in, they could take the place of all these, and these electrons would move on, and it would just keep flowing. That's why electricity flows through metals so well. So this is a little animation that kind of gives you an example of it that I found. And there's good videos out there on this in Crash Course Chemistry and Khan Academy and all those good places. So if you want to see more info on this, go for it. So this is showing how these positive ions, I tried to draw on it, I can't, but all the positive ions you see, the gray circles, stay put while all these new electrons flow through and take the place of the electron that came before. So that's why they're good at conducting electricity. So metallic bonds, they exist because these positive metal ions are sharing electrons. That sea of electrons that surrounds them allows them to be malleable, it allows them to be ductile, and it allows them to conduct electricity well. Thank you so much, guys, for watching. I'm going to probably be banging out a few more vids tonight to help us review for our quiz, and I look forward to seeing you in the next one.